Hi everyone. So today we're going to talk about the syntax analysis. So we're going to be covering, starting with the introduction, and then we will talk about the lexical analyzer. Then we will move into the syntax analyzer, and both together, the lexical analyzer and the syntax analyzer will be under the umbrella of syntax analysis. So just a quick reminder about the compiler. You know that we started by saying that the two component of the compiler which are responsible on the syntax are the lexical analyzer and the syntax analyzer. And last time we said when we want to start talking about the meaning of a sentence, the meaning of a string, uh, the output of the input coming into the semantic analyzer will be already assumed that there is no syntax error in it. Today we're going to go a bit into detail talking about what's happening in the syntax analysis stages. A compiler is an application that reads a program written in source language and then translated into the target language. That's the target language, which is the machine language. Now, also, we said compiler operates into what? As in phases, and each phase transforms the source program from one representation to another. We'll start with lexical analyzer. It feeds into the syntax analyzer and then feeds the semantics and so on. Now, the part of the compiler on which we'll focus today is the syntax analyzer or the parser. So we're going to talk about the difference between the two. We're going to cover, of course, the lexical analyzer, but we're going to go a bit deeper into the syntax analyzer. This being said, guys, this is not a compiler course. Usually, if you're taking a compiler course, you're going to go into much more detail about the steps, the exact steps of parsing and all of these things. But here, because we're just talking about the concepts or the fundamentals, the programming languages, we're going to cover them, but not in so much detail. But it will be enough for you to understand the concepts. So, syntax analysis. The syntax analysis portion of a language processor nearly always consists of two parts. What are these two parts, guys? We just said that it is going to be the lexical analyzer, which is responsible for what? For the low level part, which are the symbols, and we're going to name them as lexemes or token, correct? And then what is the other part of this syntax analysis is when the statement, the string that is already passed through the lexical analyzer is being now checked for its grammar, correct? So we're not looking at each symbol anymore. We're just checking if this whole statement has a syntax problem regarding its grammar. And we said also, how do we represent the grammar? We wanted to be more focused on the context-free grammar, which can be represented by the BNF. Now, what is the advantage of using BNF to describe syntax? Just quickly, we already covered this. I want you to just refresh your memory. Uh, BNF is what? Is that we're taking this grammar and we're writing them in a very specific way for the parser or the syntax analyzer to be able to read them better. So that means it provides a clear and concise syntax description. And what also, it will also help the parser um, uh, to be based directly on this BNF, which will be much precise, much easier to read it, and also it will be easier to maintain, of course, because, and what do we mean by parser here? We means the syntax analyzer. So syntax analyzer and parser are the same thing for us. Okay, so if we have a specific BNF, it will be easier for us to follow and maintain this parser. Now, you may be asking yourself, if both of them are part of a syntax analysis, why don't we just do them together? Why we're separating them? Why we're analyzing the lexical separately from the syntax analysis? There's three main reasons for that. There's the simplicity, and then there's the efficiency, and then portability. So if we want to start with simplicity, what do you mean by simplicity? Let's take this as an example. So this example is if, then we'll have x less than 10. So when it comes for the task of the lexical analyzer, what is the task here? The task is that we're going to check the first word here, if, then we're going to check this symbol here, and then we're going to check X. What are we checking here? We check, okay, X is what is an identifier. The less symbol is what is an operator. So the task for the lexical analyzer is much simpler, right? We're just checking one by one, and we're checking what is this? Is it an identifier? Is it a parenthesis? Is it an operator? So technically, the lexical analyzer breaks up a sentence like this, and then by keeping this simple task separate from the syntax analyzer, we can focus only on checking if the structure of the statement is correct when it comes to the syntax analyzer, correct? So here the lexical analyzer will be just checking one by one, and then the syntax analyzer will be responsible to check the whole thing, which is a bit kind of more complicated. Why? Because there will be a grammar, specific grammar that is defined, has to check if this matches the grammar. For example, why wouldn't this match a grammar if we're, let's say, doing if string is less than 10? That doesn't make sense compared to the grammar. But the lexical analysis is much more simple. So it's better to just separate the two. And this is, as we mentioned, lexical analysis is responsible for identifying the basic building blocks, whereas the process is more complex when it comes to the syntax analyzer. Now, the other aspect or the other reason may be efficiency. When we talk about efficiency, we talk about we want something to be more efficient. That means what do we want? We want to optimize it to be more efficient. Now, when should we put effort and resources to optimize something? If it is beneficial to optimize it, of course. So if you have something that has been done maybe only once, so it is already efficient enough. There's no need for me to put more resources to actually optimize this thing, right? But what about the lexical analysis role? So, for example, a well-optimized lexical analyzer quickly recognizes tokens like while or end or var without slowing down. That will if it's well optimized. But why do we need it to be optimized when it comes to the lexical analysis? Because think about it, if you have a chunk of a code that has, for example, it has x equal 3, and then if here it has x equal whatever, and then inside it will have x equal x plus 2. So how many times there's the repeated x, right? And it's actually going one by one of all of these things. There will be thousands of line of codes. That means thousands, maybe millions of characters of symbols that's going to go through them all one by one, right? So maybe we should find a better way to make it more efficient. Maybe, for example, let's take a look and instead of just feeding the lexical analysis one by one, do a buffering input, or maybe classify everything that acts as one thing. So it is needed to optimize them so it will be more efficient. But when it comes to when it's coming to the syntax analyzer, it's looking at the whole thing and just checking this if this matches a grammar. So it's less needed to be optimized. So the syntax analyzer, as we mentioned, can then focus on higher level tasks like just verifying the structure of loops or condition without worrying about the low level details. So the lexical analysis takes up significant portion of compilation time. So that's why it's better to optimize it, whereas the syntax analysis is more abstract and doesn't need as much optimization. And this is here an actual example that I was talking about. You can check here, we have I here, we have I again, we have I. So there is so many. So when we're feeding this chunk of code for the lexical analysis, what's happening is that it's taking every single symbol separately. That means going to take thousands of symbols. So it's better to find a good way to fix this. So in large programs, these basic steps are repeated thousands of times. So how can we buffer it? How can we optimize it? There's two ways. There is more than one way of course, but one of the very popular ways are buffering input, For example, the lexical analyzer can read multiple characters at once instead of processing them one by one. This is one of them. Another option can be efficient token recognition. So instead of checking every character individually, there is more efficient algorithms that can recognize keywords like or and in a fast structure, right? For example, if you're using finite automata, this is a more efficient algorithm that can do. We're not going to cover these, of course. There's a separate course that covers usually automata and other things, but you get the idea. Now, the third reason would be portability. Portability. What do we mean by this? An example for that can be platform dependent versus independent. Let's take an idea that we're not going to go into details about that, but technically lexical analyzer is more dependent on the platform, while the syntax analyzer, this is here not analysis, it's analyzer. I will fix it. The syntax analyzer um, is platform independent. So it's better to just separate them in this case. A lexical analyzer may need to be adjusted for different operating system for Windows and Linux. And why is that? Um, because the lexical analyzer handles how a program file is read. So dealing with the platform specific input mechanism like formats of or character encoding. Um, the syntax analyzer, however, is what is platform independent because it's just checking the structure of the code, which doesn't rely on the underlying system. Okay. Again, as I said, we're not going to go into deep, but you just need to understand the bigger image here. So let's talk about the lexical analysis, which is, if we want to say lexical analysis, which is more the lexical analyzer, right? So lexical analyzer, as we mentioned, is a pattern matcher for the character string. So this is the official definition from the book. These are the slides of the book. And then we said a lexical analyzer is what? It's a front end for the parser. Correct? So what does this mean? That it's the output from the lexical analyzer feeds into the parser, which is our syntax analyzer. Now, the lexical analyzers extract lexemes from a given input string and produce tokens. We didn't cover these. We skipped them when we talked about chapter 2 of the book, which is the lexical and syntax definitions, but we're going to cover them now. So I prepared this slide for you, just for you to be able to differentiate between these two words. The best way to explain this is by taking an example. So let's say we have this statement, this string. What are we looking here? So what are the lexemes here? Each character, let's call it character, is one lexeme, for example. So results is 1, then this is equal sign is 1, and this is 1. So if I tell you what is the common thing between results, old sum, and value, they are all and identifiers. Okay, what is this? This is considered an operator. This is also an operator. So when you're feeding these, the lexemes are these, and then the role of the lexical analyzer is to take the lexemes and then produce and convert them into tokens. And let's see. So lexical analyzer, as you said, extract lexemes from a given input string and produce the corresponding tokens. So in this case, what are the lexeme? We said result equal old sum, and then it's going to produce its token, which is the identifier. Old sum also is an identifier. Also, this is an identifier. And then when it comes to the equal sign, this is a sign operator. It's the assignment operator, not the equal operator, for example. So what does this mean? In a summary, it means that the job of a lexical analyzer is to find the meaning of every lexeme and represent this meaning by a token. Now, just to keep in mind that actually, although tokens here are usually represented as an integer values when it comes to the system, right? But for us to be able to read it, we represent them like this through named constants, of course. But technically, when it comes to the machine, it's reading integers. So we're taking this and we're representing, for example, by a number 3 or number 4 or whatever. But to be able to read them, we represent them with a named constant. So be very careful when it comes to this thing. Okay, now, again, from the slides of the book, we want to mention something that in early days of compiler, the lexical analyzers often used to process an entire source program. So we'll take the whole sentence that we just mentioned before. For example, we're going to take this whole thing and then put it inside the lexical analyzer, and we're going to produce everything together, and then after that feed it to the to the syntax analyzer. But nowadays, the lexical analyzer is like a function. So that means my parser, my syntax analyzer, what's happening is that each time it needs one of the token is going to call the lexical analyzer. So the lexical analyzer is going to act like a function that can be called to input the next token. Why is this happening? Because actually it just make the program more simple and efficient. So each call of the to the lexical analyzer returns a single lexeme and its token, and the only view of the input of the program seen by syntax is one token at a time. Now we covered the lexical analyzer. What about the syntax analyzer? What is the syntax analyzer? We said it's a parser, correct? So the syntax analyzer will look at the statements from a high level, not from a low level. It's going to look at the grammar of the sentence. So for example, the same example, what is being checked here by the syntax analyzer? One of the example, let's say if I have value as a string and then I'm dividing by 100, I cannot divide a string by 100. So of course, one of the rules in the BNF would be that value has to be a number, correct? So that's what actually, so we're looking at the whole syntax of the statement instead of each um, value, each symbol alone. So of course, it looks at the grammar and, for example, the BNF representation that we covered before and see if the statement has correct grammar or not. Now, as we mentioned, the syntax analyzer main role is parsing. Okay, so now we're going to talk about what is the parsing problem. So part of the process of analyzing syntax that is referred to as syntax analyzer and is often called parsing. So whenever we say, again, if I mention parser or a syntax analyzer are the same exact thing. Now, the goals of the parser given an input program is what? You should know this by now. So what are the goals? Of course, it's find all the syntax error, but not just find the syntax error. Also, it would return the error. It should give me an appropriate diagnostic message and try to recover quickly. What do you mean by recover quickly? We want to continue also searching for other problems. We don't want to find one problem and then that's it. We go home and I'm done my job here as a parser. No, we want to recover and continue searching for more errors. So of course, recovery means it must get back to a normal state and continue its analysis of the input program. This step is required so that the compiler finds as many errors as possible during a single analysis of the input program. Now, what is something very important other than just finding the syntax error? What did we do? We said we are going to do the BNF, we parse it, and we produce a parser tree. Why a parser tree is important for us? Because if you remember, we mentioned it will help us visualize, but also it will help us um, track ambiguity. How can we track ambiguity through a parse tree? Exactly through the if we have more than one parse tree, that means this definition, this grammar that we're using, this rule is ambiguous. It should only be able to produce one parse tree, so it be unambiguous, for example. So parse tree are very important for us. Let's take an actual example to be able to understand this concept better. We'll take a parse example from scratch. So we want to take this code as an example, x equal a times b minus c. So what's going to happen? The first thing, the lexical analyzer is going to output what? So these are considered what, guys? Are these lexemes or tokens? Of course, they are lexemes. So if I'm feeding these lexemes to the lexical analyzer, it's going to produce for me tokens. So X, A, B, C are what? Are identifier, for example. So it's going to produce something like this. This is an identifier, this is an identifier, and then also, of course, it's going to change this equal to a more constant naming and stuff. So this thing here is going to be fed to where it's going to be fed to the parser. Now, we said it's going to be fed one by one, token at a time. It's not going to be fed like this. It's going to be fed token by token, and then the parser will go. The output of the parser is what is a generate a parse tree. How can the parser, guys, generate a parse tree? It will need grammar. So it's going to take this from the lexical analyzer, it's going to match it with the grammar that it has to be able to produce a parse tree that whatever it looks like. Very good. Now, how is this happening? So we already covered these in the past sessions, but how is this happening? So the parsing, it there is two category of parsers, right? So there should be, and we mentioned them last time, the top-down, which produce the parse tree beginning at the root. It will start with what? With the start symbol, which will be a non-terminal, right? And then it's go left most derivation. And then the other one that we also covered, and we talked about it in a bit, is the bottom-up tree, which we're going to see that it's going to be a reverse of the rightmost derivation. We're going to see them both. So useful parsers look only one token ahead, as we said. Now, this is a summary of the parsing problem. We said in a top-down parsing, the construction starts from the root, of course, and then the bottom-up, it starts at the leaves. Now, efficient top-down parsers are easily built by hand. The bottom-up parsing are more complex to build, but they are able to handle a larger class of grammars. So let's see an actual example and different approaches. So let's assume that we want to derive this. I want to derive A, B, C, D, E, and this is my grammar here. I have S, which is my start symbol. Give me A, B, E. Now, what are the A, B capital letter? What do they represent? Of course, they represent the non-terminal. So usually because this is not BNF, right? This is general grammar description. And the general grammar description, the capital letters are representing non-terminal, of course. And then in the BNF, we represent them in a different way. So if I want to derive this using a top-down approach, I'm going to start by what, guys? I'm going to start by the S, which is going to give me A, B, E. Now, how can I go after that? I have two non-terminals, so I have to expand the non-terminals. My goal is to reach this that has zero non-terminals in it, that's only terminals. So should I go expand the A or the B? The idea behind the top-down, the top-down is to go left. So we're going to always go start from here. So what's going to happen now? I'm going to go here. I can either choose A or A, B, C. If I choose A, I'll end up with what? A, B, E, which is, I will lose these two. So of course, I'm going to choose this one. Now, what do I have? I have A, B, C. Then I still have this non-terminal. And then I'll choose now the second option here. And I'll end up with A. Am I done? Should I go home? Of course not. I should finish that job, which is I still have this non-terminal that can only be expanded as D. So this will be my last thing. Now, I built my parse tree. How would the parser, now, how would this be read? So I have a parse tree, but I need to read it, of course. So it's going to be read from leftmost. That's why top down, I always read it from leftmost. What do we mean by this? So we're going to start, guys, by having A, B, E. We're going to start. This is simple for us. Now, because we need to always start from leftmost derivation, we're going to read it from the A. So we're going to expand this A. In this case, now I have A. I expand it to what? To A, B, C. Then I'll leave B and E for the first round. Okay, very good. I can't go to the B yet. The same way I built the parse tree, I'm going to read the linear one. It's going to be different for the bottom up. That's why we need to focus a bit here. Then the A, I can only read it as A. So what is it now? It's going to be A, B, C, and then B, E, and then B is left as this one. Now, if I want to take a look at the bottom-up approach, how should I start? I should start from the bottom. That means I should start with this, with the leaves, and then go up. Now, I need to try to reach this S. This first A, if I have here an A and I have an E. So these two, I should leave them, right? So I'm going to skip the first A and go to the second A. I want to reach this A. If I'm here, now I'm on the right side, I want to convert it to this A. So this is going to be what? This A. Very good. Now what else? I'm reading here A, B, C. A, B, C. I'll just convert them to A. So that means this is going to be what? A. Am I done here? I have A, and then D, E. No, I want to have B. So now I'm just going to convert this into B, and then I can reach the C, correct? Like this. Okay, so let me erase this for you. And again, go back here, and we have this. Now, I want to read it. So this is the parse tree. You remember from data structure, we say, okay, when we define a tree, we need to read it. Usually there's an in order, post order, pre-order, things like that that we learned. So we have to also define a traversing for this tree to read it. So we said here, when it comes to the top down, we're going to read leftmost, but here, let's see how we're going to read it. So of course, in the beginning, it's A, B, E. I should always start from the B when I'm doing the bottom up approach for me to be able to end up with this one. So in this case, I'm going to start with B, I'll transform to D, and then now I'll go to this A, which will be what? A, B, C, as you can see, and then I'll go to A. If I start with A, things are not going to look good. Okay, guys, so remember, top down, we start from the leftmost, bottom up, we start from them. But what do you mean we start? We start when we read this tree. When we read the tree. When we're building the tree, we're always going to walk from the left. But when we're reading the tree, no, we read it from the right when it comes to bottom up and then left to top down. You're going to get used to it when you try it. So now let's take a look at the classification of parsers. Do you remember when we covered this lecture and I used the bottom up and the top down and I only used one thing and I told you for now, for the tutorial, just go always from the left when you're building a bottom up because we're going to learn about more different types. And as you can see here, you're going to have LR0, SLR1, LALR, SCLR. So there is many different ways to use the bottom up parsers. But first, we're going to start with the top-down parser. So for the top-down parser, these are the most two popular ones. Of course, there's the backtracking, there's too many things. But again, as I said, this is not a compiler course. So we're just going to cover a bit of the basics and fundamentals of things. So the first one that we're going to talk about is the recursive descent parser, which we already mentioned. We're going to just mention it in more details. And then we're going to talk about something called LL1 parser. And then we move to the bottom-up parser and we cover a bit of that. So for this recording, I'm going to leave it till this. We'll create a different recording to start covering the recursive descent parser.